Eigenvalues and Eigenvectors, presented by Instructor Anthony. This will consist of a lecture regarding the eigenvalue problem and its applications. So, without further ado, let us begin. Let's speak about eigenvalues and eigenvectors. Let's consider the linear transformation L mapping from V onto itself, where V is a vector space. Now we're going to consider the case where V is finite dimension, and we have A as a matrix representation of the linear transformation. So A is a square matrix because V is finite dimension and it's represented as Ln. Okay, so A is square matrix, and we try to solve AV equal to lambda V, right? And V is a non-zero vector specifically because if V is 0, it's the null vector. It's not of particular interest because lambda can be any value. Lambda is a constant. It's coming from a scalar field F, and a field is just this entity that has addition, subtraction, division, and multiplication. There are many properties such as the existence of an additive inverse, a multiplicative inverse, etc. But I will not get into that in this discussion. Okay, so we can subtract lambda v from both sides, so AV minus lambda v equals to 0. And we can rewrite the lambda v term in terms of lambda times the n by n identity matrix, right? Because when we multiply the n by n identity matrix by a scalar, then we have a set of scalars along the diagonal. And this corresponds to multiplying each entry in vector v by those scalars. It's the same scalar, lambda, right? Because AV equals lambda v. So each entry in vector v gets pre-multiplied by lambda. Okay, so if v is a non-zero vector, then the determinant of A minus lambda times the n by n identity matrix must be 0. The reason why is because A minus lambda times the n by n identity is singular, right? Okay, so when we solve for this determinant and set it equal to 0, we obtain something referred to as the characteristic equation, represented by P lambda. Now, by the fundamental theorem of algebra, this polynomial is of degree n and has up to n complex roots, not including repetition. So some of these roots could be repeated. So we can factor the polynomial lambda minus lambda 1, and we keep multiplying all the way to lambda minus lambda n. Some of these roots could be repeated. This is the characteristic equation. We call V the eigenvector associated to this system, to the matrix system A, and lambda the eigenvalue, respectively. This is also referred to as the characteristic vector and the characteristic value. Now, the ordered pair, lambda and V, form the eigenpair or characteristic pair. Okay, so let's look at the algebraic multiplicity. Now, some of these eigenvalues could be repeated. So for instance, if we have an eigenvalue with a value of 1 and it's repeated twice, that eigenvalue has multiplicity too. Now, the multiplicity of each eigenvalue can be as low as the number 1. It can be as great, as highest as the number n. So each multiplicity must be between 1 and n, right? And the total algebraic multiplicity, which is the sum of all those algebraic multiplicities, is equal to lowercase n, which is the dimension of that vector space, right? Okay, but we just defined the algebraic multiplicity as the greatest positive integer such that lambda minus lambda sub I divides p lambda. So if 1 is an eigenvalue with multiplicity 2, so it occurs twice, definitely lambda minus 1 divides p lambda, the characteristic equation, but it can be divided again, so it will be squared. So suppose that we have a eigenvalue with multiplicity of the value of 1. This is referred to as a simple eigenvalue. If the algebraic multiplicity equals the geometric multiplicity, then we have a semi-simple eigenvalue here. And the geometric multiplicity is defined as n minus the rank of a minus lambda sub I times the identity. So this is the nullity, or the dimension of the eigenspace corresponding to that lambda. Okay, so remember that V is a vector space, and we have an eigenpair obtained by solving the eigenvalue problem AV equal to lambda V. Now, the eigenspace corresponding to a particular lambda, remember there could be up to n of them, is as follows. It's the set of all possible vectors coming from vector space V such that a minus lambda times I sub n times V equal to 0. So we're solving for the null space of a minus lambda times the identity. Okay, remember that there are up to n different eigenvalues. And because the null space is a subspace of the vector space V, then we can take the nullity, the dimension of the subspace, right? And we know it must be less than or equal to n. Specifically, it's n minus the rank of a minus lambda I by the rank nullity theorem, because those two subspaces are orthogonal. Okay. The geometric multiplicity is the greatest number of linearly independent vectors in the eigenspace corresponding to lambda sub I. So it's n minus the rank of a minus lambda I times I sub n. And that's the geometric multiplicity of lambda I, and it's with respect to the matrix A. If it's a different matrix, we have a different set of eigenvalues and a different eigensystem. The eigensystem just consists of all the eigenvalues and the eigenvectors. Okay, now we can add up all the geometric multiplicities for the first eigenvalue, for the second, all the way up into the nth, right? And if this equals the algebraic multiplicity, the total algebraic multiplicity, which is obtained by adding up all the algebraic multiplicities of each specific eigenvalue, then we have a very unique property, and A can be Let's speak about the eigenbasis. So if the total geometric multiplicity is equal to the total arithmetic multiplicity, then it follows that we can diagonalize the matrix A. And so it's diagonalizable. What this means is, first, those eigenvectors form a linearly independent set. So that means that they cannot be written in terms of each other. One cannot be written as a scalar multiple of the others belonging to that set. And because there are n of those eigenvectors, we know that this is a maximal set in the vector space V. The eigenspace E is a subspace of V, but they have the same dimension, and this is linearly independent. Therefore, this eigenbasis, this set of eigenvectors forms a basis. It's referred to as the eigenbasis on that vector space V. Okay, so A is diagonalizable, and we have a similar matrix, capital lambda. So this means that we can rewrite A in terms of x, capital lambda times x inverse. And remember, x is non-singular because the columns, which are the eigenvectors, form a linearly independent set. So there's full rank, and it's a square matrix. Okay, now since A is similar to the diagonal matrix lambda, they have the same set of eigenvalues and the same characteristic equation, right? And we also have this property, A times x of I is equal to lambda xi, where xi is the ith eigenvector. Okay, so furthermore, we have another property. It's not listed here, but if A is symmetric, which means that A is equal to its transpose, we can actually develop an orthonormal basis. So the columns of X, which are the eigenvectors, will be orthogonal to each other. And we just normalize it by dividing by the norm. So each column will divide by its corresponding norm. And so we can develop an orthonormal basis. So that will conclude this discussion on eigenvalues, and I'll provide some examples in the next discussion.